Mr. Morris. It's me and Arjun. We're at the mall. We're doing the extra credit. Um, Here's the scale we're using. We got some.
So why did the weight go down? Well, the elevator was at rest and it needed to go to a constant negative velocity. So what needed to happen was the elevator needed to accelerate in the negative direction. So we can set up the equation sum of the forces in the y, or E sum F of y, is equal to Fn, or the top force, plus mg, or the negative downward force, equals negative mass times acceleration. And if we bring over the mg, Fn is equal to mg minus ma. And what the elevator displays is Fn, not mg. mg is your weight on Earth, but it displays Fn. And in this case, mg is getting smaller because of the negative acceleration. So your normal force, or what the weight displays, is a decreased weight. And the free body diagram for this shows that as the upward force, or Fn, is smaller than the downward force, or mg, so the elevator accelerates in the negative. Unfortunately, what happened, we were unable to capture footage for constant velocity because uh, we were at the mall on a Saturday, so there were a lot of people. And what happened was, since there were a lot of people, there was a stop at every single floor. So what would happen on the elevator is that it would accelerate up, and as soon as it accelerated up, it would start accelerating down because the distance from the first floor to the second floor isn't that big, so there wasn't any time for the elevator to reach a constant velocity, and therefore we couldn't capture footage of it. But what should have happened was, say per se, um that the elevator was longer, the acceleration would have become 0. So we could have set up the equation E sum F of y is equal to Fn minus mg is equal to 0. Carry over the mg, and Fn is equal to mg. So the scale would have read your normal weight as it would when you are at the doctor's office, or just when you weigh yourself at home. The free body diagram for this middle part of the elevator trip shows normal force in the positive, in the y in the positive, and it shows the force of gravity in the negative in the y. And these two forces are equal to each other, so there is no acceleration. The final part of the going down trip shows so since the elevator is going down with a negative velocity, a positive acceleration is needed to bring it to 0. So therefore we can write the equation E sum F of y is equal to Fn minus mg equals ma. And therefore the normal force is equal to the force of gravity plus ma, because it is positive. So therefore you're adding to mg, which is the normal weight. So normal force appears to be larger than it should. So it shows the scale reading increases and shows a greater weight. The free body diagram for this part of the trip shows Fn in the positive, which is greater than mg in the negative because it's accelerating positively. The positive force has to be greater than the negative force, such that the elevator comes to a rest.
Alright, this is the explanation behind the first part of motion for the elevator. So when the elevator starts to accelerate up initially, the weight, this is the explanation for why the weight is greater in that moment of time. So if you look at the free body diagram of the elevator at rest, there is no acceleration, therefore you have the sum of y, therefore sum of the y equals mass times, so it will be mass times acceleration, which is 0, and then you have here, therefore you have Fn mg is equal to mg, and it should be the same numerical value. And if you look at the moment of time when the elevator starts to accelerate, the Fm will be greater because there is acceleration this time. So if you look at the sum of the y forces equation, then you would have to, in order to solve for Fn, you have to add mg, which is negative, so it becomes positive. You add that to over here, and the result will be this. So you can already tell that Fn would be, Fn in this case, when it's starting to accelerate, will be greater than the Fn when it's at rest. Alright, so this is the free body diagram and explanation for the point in time when the elevator is moving at a constant speed. So right after its initial acceleration, this is how the Fn is going to be affected. And if you look at it, it's moving at a constant velocity, therefore the acceleration is 0, and you can conclude that with the sum of the y forces, that Fm equals mg, and that's because it's essentially the same conditions if it were at rest. So this is primarily based on the assumption that there's no acceleration and it's moving constantly. Alright, so this is the final part of the motion in the elevator. So up to this point, the elevator is going to, previously it was moving in the positive direction upward, so to bring it to rest, the acceleration would have to be negative, and if the acceleration is negative, then if you look at our sum of the forces equation, you can see that the Fn is going to be less than the Fn if the elevator was at rest, because to subtract mg minus mass times acceleration. So to conclude, the Fn is going to be less than less than the Fn of the elevator at rest, and you could see it clearly through the free body diagram and the equations. Let me just write. The acceleration should be downward to bring it to a rest, since it's going up in the positive direction.